to Calculus 1 video lecture number 9 on differentiation formulas. Now, in the previous lessons, we looked at how to find the derivative of a function at a certain point using the limit definition. And we also learned how to find the derivative as a function using the limit definition as well. However, now we're going to look at some formulas that allow us to differentiate a lot more quickly without having to apply that limit definition every single time. So here are some of the first few to get us going. The first one being the derivative with respect to x of some constant c is equal to 0. So c here stands for a constant. And this should make sense because basically you're differentiating y equals c, right? A constant function. And if you were to graph it, it would just be a horizontal line. And we know that the derivative represents the slope of the curve of the tangent to the curve at a certain point, and the slope of this line is 0 throughout. All right. Similarly, next differentiation rule is that the derivative with respect to x of x is just 1. Again, this should make sense if you think of the graph in terms of slopes of tangent lines because you're dealing with y equals x, and we know the slope of this line is 1. More generally speaking, the third rule, if you're going to differentiate with respect to x raised to some power n, what you do is you bring down that exponent in the front, n, and you multiply by it, and then you subtract 1 from the exponent. So this we call the power rule when we differentiate. Nice. Now the fourth rule, notice if you're differentiating with respect to x, a constant times some function, the constant just comes along for the ride, it gets multiplied outside, and you just differentiate the function as you normally would. And then the last rule that we have is if you differentiate a sum or difference of functions, you basically just differentiate term by term across the sum or across the difference and add or subtract the result together. All right, we're going to add to this list, don't you worry, but this is enough to get us going for this section here. So, first few examples, we're going to differentiate the following functions. First one being f of t equals 1/2 t to the 6th minus 3t to the 4th plus 1. All right, so to indicate I'm taking the derivative, I'm going to write f prime of t equals, and then now for this first term, 1/2 t to the 6th, I actually have to use a combo of this rule here where I differentiate a constant times a function and the power rule. So 1/2 is just going to hang out, times, and then now I take that exponent 6, I'm going to apply the power rule, bring it down in the front, and then I'm going to go back to t and then subtract 1 from the exponent. Good, so that's the first term taken care of. Minus, now I'm using this last rule here where I'm just going to differentiate across this sum and difference of terms. 3, just leave the 3 there, it's not bothering anybody, times, and then same deal here. So you're going to bring the 4 down in the front, multiply by it, and then decrease the exponent by 1. So now I have t to the 4 minus 1. Plus, and then the last term is just a constant, and the derivative of any constant is 0. And so we're done. The calculus is over. Now we just have to clean up our final answer. Good, so let's take a look here. We have f prime of t equals 1/2 times 6, that's going to be 3t to the 5th, minus, this is going to give me 12t cubed. And I don't need to put plus 0. And we are done. All right, looks good. Next example, we have h of x equals x minus 2 times 2x plus 3. So before I can start differentiating term by term, I actually need to distribute this product here. So h of x equals 2x squared plus 3x minus 4x minus 6. So h of x is 2x squared minus x minus 6. Now this is the function I'm going to differentiate. So h prime of x is going to equal, leave that 2 there, then you bring this 2 down in the front and multiply by it, and then you have x to the first. Decrease the exponent by 1. Minus, derivative of just x is 1, minus derivative of a constant is 0. So we're done. Our final answer, h prime of x, is equal to 4x minus 1. Can you believe it? Not bad, huh? Now, if you can just get there a lot sooner without having to show all that work, that's totally fine. In fact, I want you to get there sooner than later, because we're going to be needing to differentiate rather quickly in some later lessons. Okay, example 3, we have y equals x squared minus 2 radical x divided by x. So in this situation, we can simplify quite a bit before we actually start taking the derivative. Notice I have a radical x. I want to rewrite that using rational exponents, and then I'll show you what to do to deal with that fraction in just a second. So first things first, I'm going to write this in x squared minus 2x to the 1/2 over x. And then now, since the denominator only has one term, I can split it and write it under each of the terms in the numerator as x squared over x minus 2x to the 1/2 over x. Nice. So let's see here, x squared over x, that's just x, minus 2, and then you remember your rules of exponents. I have x to the 1/2 minus, this is x to the first, we don't write the 1, so that's going to be x to the negative 1/2. Beautiful. Now this is in derivative friendly format, meaning it's ready to go. We can just differentiate term by term really easily. So let's see here, they gave me y equals, so you could write y prime or dy dx, it doesn't matter, unless they specify in the directions, okay? Then be obedient. So I'll just write dy dx equals, now derivative of x, that's just going to be 1. And then I have minus 2, that's just hanging out, times, now be careful here. So negative 1/2, I'm going to bring that down in the front and multiply by it. And then I have x, remember the power rule, it doesn't change if you have a rational number for your exponent, to the negative 1/2 minus 1, right? You're going to subtract 1 from the exponent. Okay, cleanup time. So dy dx equals, just bring down the 1, and then negative 2 times negative 1/2, if I multiply that, that's going to be positive 1. And then I have x, what's the new exponent going to be? Negative 1/2 minus 1, that's negative 3/2. Okay, and then we can clean this up a little bit if you want to write it as 1 plus 1 over x to the 3/2. If you want to rewrite it using radicals, knock yourself out. I don't particularly care, because most of the time, as you'll see later in the unit, we're going to use the derivative for something. And so you're going to have to clean it up depending on what its use is for you. Very nice. Let's look at this next example. Look at us taking things to the next level. V equals radical x plus 1 over cube root of x squared. So first things first, we got to get this thing in derivative friendly format. It is not looking very friendly at the moment. I'm going to rewrite this. This is v equals rad x. I'm going to rewrite that as x to the 1/2 plus, now 1 over cube root of x, that's x to the negative 1/3. And this all gets squared. Good? Got to remember your rules of exponents. That's why you sat through precalculus. That way you'd be ready to roll right now. And then we have to square this quantity. So let's remember our rule. You square the first term. So I have x to the 1/2 squared plus 2 times the product of a and b. So 2 times x to the 1/2 times x to the negative 1/3 plus, and then you square the last term, x to the negative 1/3 squared. Okay, let's see what we've got going on. So x to the 1/2 squared, that's just x, plus 2 times x to the, now let's see here, I have 1/2 times -1/3, so I'm going to add them together. So 1/2 minus 1/3, that's 3/6 minus 2/6, so it's going to be 1/6. So the new exponent here is 1/6. Plus x raised to the, now I'm taking a power, raising it to another one. So for our exponent rules, I multiply x to the -2/3. I'll put the 1 here if it makes you feel better. Okay, so it looks like it's derivative time. Let's go term by term. So we have v here. All right, v prime is equal to, so derivative of x to the first is just x. Oh, excuse me, just 1. Plus 2 times, so you bring down the exponent 1/6, multiply by it, and then you have x to the 1/6 minus 1. We'll clean it up in a minute. Plus, same thing here, bring this exponent down in the front, so I have -2/3 times x to the -2/3 minus 1. And then now we're ready to put it all together. So v prime equals 1 plus, this is going to be 1/3 x raised to the -5/6, 1/6 minus 1, minus 2/3 times x to the -2/3 minus 1, that's minus 3/3 from it. So this is -5/3. Okay, and then let's clean it up just a smidge more. So v prime equals 1 plus, I could write this as 1/3x to the 5/6 minus 2/3x to the 5/3. Okay, if you're unsure how far to simplify, just use the answer guide in the back of the book to the homework exercises as reference for what the standard is. And like I mentioned earlier, most of the time you're going to use the derivative for something. And when we get into finding critical values, maximum, minima, you're going to have to clean it up to a certain point in order to do that. So you'll naturally know how far to clean it up. But in the beginning, just check your answers as you do your homework exercises and use that answer key as the guide as to how far to simplify. All right, so now that we've got the power rule down, let's expand our repertoire of what sort of functions we can differentiate. And we're going to work on exponential functions now. How exciting. So if you'll remember, you should have seen this in pre-calc, hopefully, that 1 plus 1/n, that quantity raised to the nth power, approaches E, Euler's constant, as n approaches infinity. And E, it's an irrational number, much like pi, and it's approximately equal to 2.71828 ... Okay, we will actually later in the semester show that this is the case using fancy schmancy limit laws. Also, definition of E, Euler's constant, for the calculus student. We define E to be the following. The limit as h approaches 0 of e to the h minus 1 over h is equal to 1. This should remind you of what we worked on in the last unit when we found derivatives using the limit definition, and we're going to build on it right now. So we're going to use the above definition to find the derivative with respect to x of e to the x. Okay, so we're going to let f of x equal e to the x. And then remember how we found derivatives previously. F prime of x was equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So now I'm going to apply this definition to the function e to the x. So we'll have the limit as h approaches 0. Now f of x plus h is going to be e to the x plus h. minus f of x is just e to the x, and this is all over h. Now from here, I can rewrite the first term as e to the x times e to the h, and then I still have minus e to the x over h. Why did I do that? Because now I can factor out e to the x, so I have the limit as h approaches 0 of e to the x times e to the h minus 1 over h. Now look at this limit. This limit is dependent on h, right? H is approaching 0. There's h's here and h here. But e to the x is not dependent on h. So it's treated, or it's a constant in this limit. I can pull it outside and rewrite this now as e to the x times the limit as h approaches 0 of e to the h minus 1 over h. And does that expression look familiar? Yes, that's our definition of e that I showed you earlier. So that limit we know is equal to 1. Oh, wow. So that means this whole term approaches 1. And all I'm left with is e to the x. Oh, that's pretty snazzy. So that means the derivative with respect to x of e to the x is equal to e to the x. It's just itself. So if you differentiate e to the x, you get back e to the x. Pretty nice derivative, huh? Okay, so let's practice using our differentiation rules now. So find f prime of x and f double prime of x for the following function. F of x equals e to the x minus x cubed. Okay, so f prime of x, remember, derivative of e to the x is just itself. Minus, and then can you do this a little bit quicker now? Derivative of x cubed, that's going to be 3x squared. And then f double prime of x, just go for one more round. So derivative of e to the x is still e to the x minus 6x. Good? You multiply the 3 by 2, it's 6, decrease the exponent by 1. All right, very nice. Now we're going to look at a couple more applications. First one being tangent line and normal line. In case you haven't heard the term normal line before, the normal line is perpendicular to the tangent line at the point of tangency. So that means if you take the slope of the tangent line, that's what m tangent is, and you multiply it by the slope of the normal line, you should get -1. Another way of stating this is that their slopes are opposite reciprocals. Okay, now since we're just working with lines in the plane, in a two-dimensional plane, you could think of normal as the same as a perpendicular line, or it's going to be perpendicular to the tangent line. But we start using the term normal in math because you're going to eventually expand to higher dimensions and apply that idea not just to lines, but also to other sorts of planes and geometric shapes in space. All right, so here we go. First example. Find the equations of the tangent line and the normal line to the curve y equals x to the 4th plus 8e to the x at this point. So they gave me the point. I just need to figure out the slopes of the tangent line and the normal line, and I know I can do that by getting the derivative. So here we go, y prime, derivative of x to the 4th, that's going to be 4x cubed, and then derivative of 8e to the x is just going to be 8e to the x. So if I want the slope of the tangent line, I'll write m with a t for the subscript. I'm just going to substitute in 0 for x. So that would be 4 times 0 cubed plus 8 times e to the 0, which is 0 plus 8 times 1. So that gives me 8. Now for the slope of the normal line, I just take the opposite reciprocal. So I would flip it and change the sign, which would be -1/8. And you can see, using our definition up above, 8 times -1/8 is -1. That's a pretty slick definition, right? Instead of being so wordy and writing slopes or opposite reciprocals, you just say, oh, multiply them and you get -1. Okay, so now we're ready to go. We can write those equations. The tangent line, we have that the slope is equal to 8, and they gave me the point, it's 0, 8. I mean, I couldn't have asked for a nicer problem. This is the y-intercept, that's b. So you can just go straight to y equals 8x plus 8. Love it. And then let's go ahead and do the normal line. I mean, we didn't even need point slope form. So slope of the normal line is -1/8. Remember, that's right here. Same point. That's b. So y equals -1/8 x plus 8. Okay. Let's take a second and look at the graph so you guys can understand exactly what's going on. So here I have graphed x to the 4th plus 8e to the x. And remember, we're interested in finding the equations of the tangent line and normal line at the point 0, 8. Do you see? Let me add it back in so you can see. There's the point. Okay, so we found the equation of the tangent line to be 8x plus 8. That's right here in green. Looks good. And then here is the normal line, -1/8 x plus 8. And you could see that the normal line is perpendicular to the tangent line. That's all that that means. Good? Feel free to graph anytime you want to really understand what's going on and have a visual representation of whatever it was that you just found. Now, last example of the lesson deals with particle motion. So the example is as follows. We are going to work with the equation of motion of a particle, and it's given by s equals t cubed minus 12t. I'll say s, the position is in meters. All right, so the first part asks us to find the velocity function v of t, which, if you'll recall, is equal to s prime of t, the derivative of the position function. So we can go ahead and differentiate really easily now term by term. V of t is going to equal, derivative of t cubed is 3t squared, and then derivative of -12t is just -12. So there's the velocity function. Part B asks us to find the acceleration function, which is the second derivative of the position function. So a of t is going to be the same as the derivative of the velocity function, right? Which is the same as s double prime of t. You don't have to write all of this, I'm just reminding you of it. So now let's go ahead and differentiate the velocity function we just found. And we'll have derivative of 3t squared, which is 6t. And then derivative of a constant is 0, so that's it. All right, part C says find the acceleration after 9 seconds. So now I'm going to substitute in 9 for t. So a of 9 equals 6 times 9, which is 54. And then units for acceleration are going to be meters per second squared. It's always second squared for acceleration. And then the last part says find the acceleration when velocity is 0. So to start off, what I need to do is set the velocity function equal to 0, see when that happens. Okay, so v of t, we have it up above. It's 3t squared minus 12. I'm setting that equal to 0. So that means 3t squared equals 4. Oh, I'm already dividing in my head. Shame on me. 3t squared equals 12. T squared is 4, so you get t equals plus or minus 2. Typically, we always just take t to be positive, so we'll use 2. And so now they're asking for what the acceleration is at t equals 2. So you go back to your acceleration function. A of 2 is equal to 6 times 2, which is 12 meters per second squared. And that's it. So that concludes the lesson. Be super careful when differentiating that you apply your rules of exponents and everything properly. So if you need a little bit of an algebra or pre-calc review, take the time to do that so that moving forward, you're really strong since we're going to build on this. Don't forget to give the video a thumbs up. Stay tuned. More differentiation rules to come.